All right. Hello, everyone. I'm Conrad, one of the co-chairs for PyData Global 2024. Welcome, everyone, to day 2 of our conference and to the very first talk. I have with us T-Boot, Valentin, and Hussein from Capgemini, and they are here to talk to us about boosting AI reliability, uncertainty quantification with MAPIE. So during this talk, feel free to use the chat to connect with fellow attendees or to ask questions. There's also a Q&A tab, and I believe that Valentin will be answering the questions as we go along. So without further ado, please take it away. Thank you.
Thank you, Conrad, for the introduction. Yeah, I will start sharing my screen. Okay, and that should be it. So we're going to start with a short presentation of what's going on. So basically, we're going to talk about MAPIE, which is an open source library, a Python open source library that helps you measure, quantify uncertainty. So we will have a brief introduction about uncertainty, the mathematical framework on which MAPIE is based, and MAPIE itself, of course. And then we will go quickly into a more hands-on session. So we will share in the chat 2 notebooks. The first one will be about regression and how you can do regression tasks and measure uncertainty in that setting with MAPIE. The second one will be about classification, and at the end also we will talk about the framework of risk control. So to begin, we can talk a bit more about uncertainty and why measuring uncertainty is helpful when you're developing AI systems. So I'm pretty sure 90% of the people attending this talk are in one of these 4 personas. Probably most of you are AI designers, and of course, as machine learning engineers or data scientists or whatever, you want to understand if your model is certain about some prediction it does, or on the other hand, if your model is not that certain about it. But you're not the only one involved, right? There is also, so in like a business setting, you also have an AI operator that will actually use the model you conceived and released. So that operators is also very concerned about the uncertainty of your predictions. Then, of course, you have regulators. For example, in Europe, we have the AI Act that will be enforced in a few years. So, of course, regulators will have a look at that kind of thing. And lastly, impacted people, I mean, end users are also concerned about the robustness and the uncertainty surrounding the AI system they use. For example, with the rise of LLMs and chatbots, maybe you want to know when you ask, let's say, ChatGPT a question, maybe you'd like more answers like, to be fair, I don't know, because usually what they do is that they produce a very comprehensive answer and they are pretty confident about it. But sometimes those chatbots are just wrong, and you may want to know when they're wrong. There are a lot of methods to measure model uncertainties. They all have advantages and drawbacks. A lot of methods require a pretty strong assumption on your data. And some methods are not even model agnostic. So there is no perfect method here, but conformal prediction, which we will introduce just after, is very interesting because it's pretty simple and it's not very computationally expensive, or at least if you use the let's say the good algorithm for your use case. It doesn't require strong distribution assumption on your data. Basically, we just need the exchangeability assumption, which is let's say a weaker version of IID. So it's pretty weak actually. It is model agnostic, so it's pretty useful because you can use it with like any model you want. And very importantly, it's mathematically grounded, and it will provide statistical guarantees of what you do. And of course, I mean, as you may have guessed, MAPIE is implementing conformal prediction and helps you use conformal prediction. So let's dive a bit. Let's be a bit more specific. Let's say you have a system with a bow and that shoots an arrow, and then you have a model that will try to predict where the arrow will fall. So basically, your model has as inputs maybe your internal system parameters, such as angle and stuff like that, but also like external parameters that you can't really control. And then given all those inputs, it will try to predict where the arrow will land. So here, the operator of the model is pretty sure the system will shoot the arrow in the apple, but of course, that poor boy wants to be sure, right? What you can do with uncertainty quantification is instead of predicting a point, you will try to predict here an area. So in the first case, if you're, let's say, 90% sure that the system will shoot the arrow in the green area, then maybe you're fine with the risk and you will shoot. On the other hand, on the right-hand case, probably you don't want to shoot that arrow, right? So that's the point of conformal prediction. We are able to say, given a risk level, so let's say 5%, we are able to say, thanks to conformal prediction, okay, 95% of the time, the arrow will fall in that specific area that I predicted. And of course, in the real world, it's very useful. As I said, for example, for a chatbot, but for autonomous vehicles, everything related to medicine, pretty much every critical system may benefit from this. So basically, as I said, the idea here is not to predict a single point. So on the left, you have the ground truth in green, I think. And then in blue, you have the prediction of your model. On the right, and thanks to conformal prediction, that I will not dive deeper into how it works, but you may ask a question in the chat. So thanks to conformal prediction, you will be able to predict a set, basically, of points. And so this is the regression setting, but we will talk about how it works in the classification setting just after. So basically, we talk about coverage and risk level. The coverage is 1 minus the risk level. So let's say 5% risk level and 95% coverage. And so in the classification setting, it's a bit different because the prediction sets, so the prediction sets are actually sets, of course, of classes that your model, your conformalized model will predict. So basically here on the left, thanks to conformal prediction, you will predict that we're 95% sure that this is a fox squirrel. But then the image in the middle, we are 95% sure that this is either a fox squirrel or a gray fox or a bucket or a rain barrel. So here you can see that it's pretty interesting because you can take advantage of this additional information, and as for example a system operator, you can take a different decision. So that's how it works in a classification setting. And on the right image, basically your model will predict that the image is a marmot because the softmax is like 0.3, so it's the highest ranked class, let's say. But if you use conformal predictions, your model will output a huge set because it's not super certain about things here. And in that set, we can see that there is, in second, the fox squirrel, which is the true value. And so here, thanks to conformal prediction, you are able to capture the fact that your model says it's a marmot, but actually it's not that sure. And you also have the real true value in the output set. So after this introduction about uncertainty and conformal prediction, we can talk a bit more about MAPIE. So as I said, MAPIE is an open source library that implements the framework of conformal predictions. The idea is that, of course, it is model agnostic because conformal predictions are, and it's pretty much compatible with everything you want to use, especially, for example, scikit-learn model. We're actually in the scikit-learn-contrib organization. We're also doing other things, including risk control, because we believe it's a very important area of uncertainty quantification. And it's especially useful for real case, real world scenarios. And as I said earlier, you really have statistical guarantees about what you do. And actually in MAPIE, we implement only papers that are published by researchers. And so we're not inventing things, right? We really follow the algorithm presented in the papers. So we really try to stick to the scientific literature. So there is quite a team behind MAPIE. We have few core developers, let's say, with some full-time ones, including myself and Hussein. And we also have partnership with the industry. MAPIE started in 2021 with a partnership with Michelin. And we're currently backed by Capgemini Invent. And we're also working with so the Région Île-de-France, which is like the Paris region, let's say, because we're Paris-based. And so we're also having as partners universities and things like that. So there is a pretty big team behind MAPIE. And of course, we also have external contributors. So if you're interested and if you want to start or to continue contributing to open source, we will be really happy to help you and if you want to help us, you're of course welcome. So in MAPIE, you can find a lot of things. As I said, we implement conformal prediction for regression, for classification. I also mentioned risk control. We also do a bit of calibration. So we try to stay focused. But of course, we provide quite a lot of tools. And so now we will deep dive into the first notebook. Est-ce que tu as envoyé les liens du notebook?
Non.
So Hussein will send you the link of that notebook, which is on Google Colab. It's in view only.
Je sais pas ça.
So, dans Teams, je t'ai envoyé le truc. So it will be in view only, which is normal. It's intended, but if you want to run the notebook, you can basically, I think, duplicate it, copy it on your own Google Drive or Google Colab, so you can run the notebook. So let's install MAPIE. MAPIE is also available for installation on Conda if you prefer using Conda. And so in this tutorial, we're going to talk about the MAPIE usage in the regression setting. And we will first go through a very simple example. And then we will try to compare methods, and especially what we call cross-conformal methods with the conformal quantile regression, which is a pretty powerful method when you have heteroscedasticity in your data. Something I didn't talk about is that under the hood, when you're doing conformal predictions, you will need to have what we call a calibration dataset. And basically, because of course you need to understand how your model behave to be able to compute prediction intervals or prediction sets. And so for that, you will need to keep some data. Usually you try to get that data from the test set. And if you have more than 200 observations to spare for the calibration set, we recommend you to use what we call split methods. So basically either the cross-conformal regressor that I will introduce later, or any split methods. If you don't, there is a framework in conformal predictions that is called cross-conformal, and basically it's kind of the same as the cross-validation. So you will split your data sets into folds, and then you will train the model on, let's say, 4 folds, and the last fold, the fifth one, you will calibrate, and then you will mix things up. And so it really helps when you don't have that much data. And so today we're going to compare those cross-conformal strategies with a split one, that is the CQR. So we're importing the usual suspects. So we will define a pretty simple function, which is x times sinus x. And what we will do, so this is the function, and what we will do is that we will add noise to that function. So because the idea here is to quantify uncertainty, so we need noise at some point. Here, the noise will be constant, and I will show you how it looks. So this is just function declaration, and then this function basically helps output an entire data set. So here will be between -5 and 5 with 600 observations. And so if we plot our function, it will look like that. So the noise is constant because at any place, if you draw a line, a vertical line, it will be roughly the same size everywhere. So the first thing is we're gonna pick an estimator, so it will be a regressor, of course, and we will use a polynomial function with degree 10. It's pretty high, But sorry, this way we're pretty sure that the function will be able to match perfectly our x minus x. So what we do is just actually fitting a linear regression on some features and using the polynomial features tool by scikit-learn. Basically, we're computing a lot of features up to degree 10, and then we fit a linear regression. Yeah. Okay. So we will switch. Okay. I hope you can hear me well. Please let us know if you don't. We just switched sound from one computer to the other to avoid the keyword sound. So actually, I did a little mistake. I think it's a mistake from a previous notebook attempt. I'm not sure about how to clear the output. Yeah. So I didn't want to fit that. Let's just declare it. So now we have a regressor that will be able to fit that curve. And we will use MAPIE to be able to predict not only points, but also intervals. So what we do is just we import MAPIE regressor. And basically, as you see, it's just a wrapper around your model. Here, we're in the split setting. And we just fit MAPIE or MAPIE regressor on the dataset. So what this does under the hood is that it will split actually X train and Y train in a real training dataset, and it will keep some for calibration, as I said earlier. So here the data splitting is done directly via MAPIE. And MAPIE will also fit the model for you. If you already have pre-fitted model or pre-trained model, which is usually the case when you're like do transfer learning or just you have huge neural network that you don't want to retrain, you can use CV equal, so CV stands for cross-validation. You can use CV equal prefit. And basically you can use a model that is already fitted. And so here I will compute predictions, but also intervals. PIS stands for prediction intervals using MAPIE.predict. So as you see, it's pretty close to the scikit-learn API. You have fit and then predict. And here, as you can see, the alpha I'm using is 5%, but you can definitely change that value depending on your use case and like the real risk level you want. So I just fit everything. We can look at the shapes of our outputs. Of course, so my data set is 3. Okay, so yeah, it's 3,000 points, and so this is the size of the test data set, and the shape of the intervals array is, of course, the same size as the test data set. And the two here is basically you have a lower bound and a higher bound when you predict something. And the one here, we can forget about it. It's just that you can also pass a list in that alpha parameter if you want to use MAPIE for several risk level. And so here you will have the number of alpha. And so our first prediction is -4, 0.77, blah, blah, blah. And here I also printed the intervals, the associated intervals. So here it's -5 and -3, 8. So basically that's that's your prediction point that you would have got without MAPIE. And MAPIE basically gives you this interval. So this is just for 1 point, the first prediction. Let's plot the result for all the points. So I will not bother you with that code. It's basically matplotlib. And so here what we get is this. Basically, the blue line is our polynomial model trying to fit the training data. So as you can see, it's pretty close. We printed the training data in red to see how well the model will fit it, but it's pretty accurate, right? What's interesting is that we are able to predict the true confidence intervals because we were the ones deciding what noise to add to our function. So basically, we are able to know exactly which interval will contain 95% of our observations, basically. And so here we can see that the confidence interval predicted by MAPIE, wrapping our model, which is in blue, is pretty close to the true confidence interval. And so now, as I said, we are going to compare different methods that are provided by MAPIE. So the first method I want to introduce is the conformalized quantile regression. So that method is based on what you will need is a quantile regressor to make it work. So I'm not sure you're familiar with the quantile regressor, but basically you can use the one from scikit-learn. And so here the parameters are not super interesting, but basically alpha, I think 0 means no regularization here. And I added a quick image from Wikipedia. So basically what does a quantile regressor is that you give it the quantile you want to predict. So if you give 50%, basically it will try to predict the median of your data. So it's basically, it behaves like a usual regressor when you ask for the median. But then you can also have the quartiles, so 25% and 75%. And also like here, we're predicting. So basically what the model tries to do is that yellow line on top is basically trying to split the data between. So under that yellow line, you should have 95% of the data, and above you should have only 1%. So that's what quantile model does. And as you may have, as you may think, it's actually pretty close to what we are trying to do. But here, it's only a machine learning model. So you're never sure that those 5%, 95% are accurate, right? It's not statistically grounded. It's just a machine learning model. It could be very bad or very overfitted. So to use the conformalized quantile regression setting, you will need a quantile regressor. For all our other algorithms or strategies or methods that we implement, you can basically use any model you want. And actually, a lot of models can be quantile regressors. For example, basically what you need to minimize is the pinball loss. So any neural network model can be a quantile regressor. You just need to set the proper loss, and we call that the pinball loss because it looks like a pinball kind of. So you can check this out if you want more details. So here what we do is that we instantiate a lot of strategies Each strategy is basically one method of conformal prediction implemented in MAPIE. I will go pretty quickly over the different methods. So naive, don't use that one. Basically, it's the data leaking method where you just train on the entire data set and then calibrate on the entire data set. So it's basically leaking, but it's interesting to see data leaking and overfitting. Then the jackknife type methods. Basically, it's pretty it's pretty computationally heavy, because what we're doing is that, so all those methods are cross-conformal methods, except the last one that I just introduced. But those one are cross-conformals, and what we do here is that if you have a data set size 100, for example, we leave one observation out for calibration and we fit on the 99 others, and then we do this for each observation. So it's pretty pretty computational heavy. And then CV, it's just like the same, but this time with usual folds. So here we have, for example, 10 folds. And then you have the jackknife AB, which stands for after bootstrap. And here, instead of having folds, we're basically sampling our data here 50 times. So it's a pretty good method because it's less computationally efficient than the jackknife, and it gives pretty strong results. And here, as I said, we're instantiating conformalized quantile. So you need to specify methods quantile and CV split. So basically, this is a dictionary of parameters to pass to MAPIE. And so this is just a for loop fitting every method here to our data set using MAPIE. And so we can print the result. Okay, so basically, when you look at that, you think that all the methods are pretty equivalent, because what we are interested in here is the prediction intervals, and they look the same for almost the same for every method. And we see that every function is able to fit the data. Of course, it's the same function for every method, the same model, sorry, for every method except the conformalized quantile one. And so that's why the blue, so basically the blue line is the model itself, and we can see that it's a bit different than the other. So the polynomial function will, you can see that probably this is overfitted. So probably the polynomial function will go very wild if you try to see for other x values. Here our quantile model is maybe, I think it's also a polynomial, but it seems I don't know how it behaves, but at least it's not the same. So to understand a bit more the difference between the methods, we are going to compute the mean interval width to see how the interval widths behave. So basically, we can know we can know the true width, basically because we added the noise ourselves. So we know the exact interval width that will be containing 95% of the data. And here it's like 1.99 something. And so we can see that a lot of methods are pretty close to it. Some are a bit lower, meaning they're overconfident, because of course we have smaller intervals than the reality, meaning the conformalized algorithm is a is a bit overconfident. And of course, that's the case for the naive methods because the naive methods basically overfits. But we can see that all our methods are pretty close to the true width. And then you can see that the conformalized quantile regression behaves a bit strangely. Um, it's due to the fact that first, those methods are cross-conformal methods. So basically, they are averaging things. And the second reason is that conformalized quantile is very strong for data where you have heteroscedasticity, and it's not the case here, but we'll see that later, just after. And so what we can see is the effective coverage for those methods. So this is the real coverage on the test data set. And so we can see that the naive method is too confident, and actually the real coverage is a bit lower than the one we would like. Otherwise, all methods have almost 95% coverage, and the CQR is above that threshold. So now we will pretty much do the same, but this time with heteroscedasticity in our data. So we're using the same function, but this time we're adding some heteroscedasticity. So as you can see, the noise is larger when x is larger. Again, we fit a polynomial function, and we also fit the quantile regressor. And we do the same. We instantiate all our strategies, and we check the results. So as you can see, it's pretty fast because this was the fit. And here is the plot. Okay. So here, what we can see is that our cross-conformal methods don't have very, what we call adaptative intervals. The interval size looks quite constant, whereas what we would like is to have small intervals, because here we're pretty certain about our predictions, and here it's much harder to estimate the aleatoric part of the data. So we would have liked larger intervals, and that's actually the true confidence interval shows this behavior. But that's not our result, right? But here, if we look at the output from the conformalized quantile regression, it's pretty close to the reality. We see that the intervals are very small at the beginning when x is low or close to 0, and then it starts getting bigger. As you can see here, we have this weird behavior, but it's really due to the nature of probably the training data, because as you can see, we have pretty strong outliers here, and probably it had made the model kind of overfit, or at least, but we can see that the model is pretty adaptive. And so if we check the same graph as before with the interval width, so the true width will be that perfect line because the noise is proportional to x. We can see that all the methods are, as we said, not really good at capturing heteroscedastic noise or data, let's say, especially because some of them are actually constant. For example, the naive, the jackknife, and the CV, because by construction, those methods produce constant interval widths. Some of them are a bit more adaptative, as you can see. For example, the CV min-max, jackknife min-max, it tries to get to that higher intervals in the end. But as you can see, the conformalized quantile regression is like the best method here because it's pretty close to the true width. And so here we don't have conditional coverage. Conditional coverage is, let's say so the 95% coverage is valid for all the methods. So basically, all the methods will have a theoretically coverage of 95% if you ask for alpha equal 5. So actually, it's a bit more complicated because some methods have different coverage, but let's simplify. Here, theoretically, we're pretty sure of our coverage, but this coverage is an average on all our data. When we talk about conditional coverage, we talk about a subset of our data set that we would want coverage on. So let's say I want coverage on um, every x that is greater than 3. And here we can see that the intervals are way too small, and probably we will not get conditional coverage for the part of our dataset where x is greater than 3, because the models will be way too optimistic, let's say, about the true noise of the data. And so what we can do is actually get the coverage for each method here. And here we can see a bit more what I wanted to talk about conditional coverage. So basically, all the methods provide a very good coverage for small values. Basically, they have a 100% coverage because the intervals are very wide and the noise is like super small. So basically, if we go back to this, basically the interval is super large and the noise is very small. So of course, we capture all of our data. On the other hand, as X is getting bigger, the coverage is getting lower, and we can see that the coverage is very low for large X. Here we can see that the conformalized quantile regression is still does a pretty good job because we have conditional coverage for all those bins except the 4 or 5 bin, and still we're pretty close. So what is guaranteed with conformal prediction is the average coverage, the marginal coverage on all the data sets. To achieve conditional coverage, we implement several methods. I will not talk about it now, but we of course have a lot of methods to be adaptive because that's in real world scenarios that will be of course the case. You usually have weird data in the real world and you want sometimes conditional coverage. And so here we can see the effective coverage for all methods. And so we have a pretty good coverage, but the goal of conformal prediction is to produce the smallest possible intervals, right? Otherwise, you don't get information or the information is too vague. So for example, for the cross-conformal methods here, the intervals are very wide, so it's not really helping you. Probably you, as an operator or like part of the business, you will know yourself that the data is within that interval because it will be probably obvious for everyone. So it's not helping you, that very wide interval. And on the other hand, when you're pretty close to your data, here you really can take advantage of measuring the uncertainty of your model and using those intervals to take business decisions. So as I said, very good coverage is useless if you have a very wide range of values. Here we can see that the conformalized quantile regression interval width is much lower than the other methods with a very good coverage. So this will be the preferred method for for regression when you have heteroscedastic noise. So I will hand over the floor to Hussein, who will introduce you to classification. So this was a notebook that is in our documentation, actually. So I modified it a bit. And we have a lot of notebooks exploring different topics in our documentation that is on Read the Docs. So make sure you check this out. Yes.
Thank you, Valentin, for this great tutorial. So I will take over now to show you how we can use the MAPIE for uncertainty classification, specifically for the uncertainty quantification, specifically for classification use cases. So if I will share my screen, can you hear me well, or can you see my screen? Okay. So okay. So first, this is the collab I shared with you already, the resources. First, we are installing some packages required in collab that are not pre-installed, and we are cloning some MAPIE tutorial just because some examples are used from our GitHub with MAPIE tutorials. And so let's start. Just a quick recap about uncertainty quantification in the cases of classification. So in standard classical cases, we have an image or an input data, and we are giving prediction, one single prediction. This is good actually, but sometimes we don't want just one single prediction. We want set of possible predictions, such as we are sure about 95% or 90% of cases that their true prediction is among this set. So this is what we'd like to have, so that we are covering almost all conditions or cases. And for example, in the second image, we have we know that it's Fox squared, but we are not sure. We are only sure 82%. So we are giving other possibilities, and these possibilities will be based on some specific threshold. And then the third image, we see that we have larger prediction set because we have larger possibilities and we have lower thresholds. So yeah, so this is basically the cases of uncertainty quantification for classification. And so what we will show you in this tutorial is how to use MAPIE for the case of classification, how the number of classes vary according to the significance level or the confidence level, how to make sure that the conformal method is well calibrated, and what are the pros and cons of different conformal method used for the classification. So another quick recap of the conformal framework, conformal prediction framework. Our initial data set will be divided into three parts. We have the calibration set, 50%, 15%. We have 70% training set and 15 test set. And the first step is that we are training our model in classical way as we train our scikit-learn model, for example, the random forest. And in next steps, we came the calibration phase. So we have three steps in the calibration phase. First, we apply the prediction on the calibration data set. We just predict our data and we get our predictions. The second step, we obtain list of non-conformity score. A quick recap of what is non-conformity score. It's basically a scalar value, a score value that measure how much the data point is conformal to the training data set. So, for example, if we have non-conformity score that is very high for one specific data point, we say that this data point is not aligned or it's very different from our training data set. And if the non-conformity score is very low, we say that the training data point is aligned with our training data set. We can think about also non-conformity score like errors, like some kind of similar measures to how we are calculating errors when for predictions. We have many options for non-conformity score. One option is in the case of the classification is just use 1 minus the softmax of the true label. So if this value is high, it means like we are not aligned, and if the value is low, it means like we are aligned with the data point is aligned with the training data set. And the fourth step in the calibration phase is that we calculate the quantile and the 1 minus alpha quantile of so the 1 minus alpha means like the confidence level. So alpha is a significant level. For example, it could be 10% or 20%, and 1 minus alpha is the confidence level. So this is the most important step. We calculate the quantile, and based on this quantile we will do our prediction for the test set. So in fifth step for the test set, we calculate our prediction, and then to calculate the conformal set, we just take we compute the non-conformity score, and we take all possible values that have non-conformity score lower than the quantile. I will just get back to the chat to make sure that you are hearing me correctly. Okay, so I will make the notebook larger. Okay, is it good for now? Okay. 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 So this is basically the framework of conformal prediction, but we don't worry about this at all. All this will be done in the back end of MAPIE. You just call fit and predict in MAPIE, and it will do the rest, and just you define the parameters. So first we will create our toy data set. So the image of our toy data set will be like this. We have three labels: the blue, the red, and the green. And so we have three sets that we are trying to make classification distinct between them. And we will use conformal prediction in case of uncertainty. We see that in the center we have the highest mix between the three data set. And so in the center will be we will have the highest uncertainty, but otherwise in the rest we have like we will be pretty sure about our prediction. And so to create this toy data set, we'll start first by creating the centers of each circle or of each data set, and then we will define our covariance. And these are some parameters, the number of samples and some other parameters. And for creation, we will sample using multivariate normal distribution using the centers and the covariance and the number of samples. And one of the most important part is that we have our data set. We will divide it into three parts: the train, the test, and the calibration. So first we divide into train and test, and then we divide into train and calibration. So we have three data sets, and we are just making some concatenation. And here's just some instruction for plotting. So yeah, so that's it. And later we will show how to use MAPIE using the prefit mode. So we'll assume the user already prefit random forest or Gaussian model or any other scikit-learn model, and then we will apply fit and predict using MAPIE and see how it will calibrate, making the calibration. We have three options for conformal prediction and classification. The only difference between them is how we are defining the non-conformity score. So all three of these methods are using the same framework of conformal prediction present in this image, but just the only difference is in terms of how we are calculating the non-conformity score. So, for example, in the label method, the non-conformity score is just 1 minus the softmax of the true label. So we calculate the 1 minus the, so here we have 0 is the true label. We calculate 1 minus the softmax. We have, we evaluate this non-conformity score on all calibration data set. We calculate the quantile based on the 1 minus alpha or the confidence level, and we select the values that are lower than the threshold. This image is a little bit misleading because here we are using softmax and not 1 minus the softmax. So instead of taking values that are lower than the threshold, we are taking values that are higher than the threshold. But essentially, we just take the non-conformity score, which is 1 minus softmax. At the end, it would be the values that are lower than the threshold. The second option of non-conformity score is adaptive prediction set method. Essentially, here we use the cumulative sum value of softmax. First, we order the softmax in decreasing order. So first, we start by the highest one, which is 1 here, the label 1. Second, which is the 5, the label 5. And we add, we make cumulative sum over the softmax. And then so this is the non-conformity score. Higher value of cumulative sum means that the value is coming at the end, and it's the value is coming at the end. It means that it has lower non-conformity, low softmax, and low softmax. It means it's not aligned with the training data prediction. So we take the true class. The true class is 0 here. The non-conformity score of the true class label. We analyze for all calibration data set. We have we get the quantile, and we have the threshold to make our prediction set. The third method is the top K. So we just use the rank, nothing else. So we rank the rank or the order of the true label, and we calculate the quantile, and we have our prediction data set. Later, we will see that top K will always result in same size of prediction set. For example, if the quantile is a 3, it will be always 3. For example, we'll see later and show a concrete example on this. So let's start with the first method, the label method. So as we said, the conformity score will be 1 minus the softmax of the true label. We calculate the quantile of all non-conformity score on the calibration data set, the quantile of 1 minus alpha quantile. Here we have some small correction, n plus 1 over n if we have a small data set, but essentially it's 1 minus alpha quantile. And the prediction set of on the test set, it will be where the conformity score is less than the quantile. In other words, we have the softmax is higher than 1 minus the quantile. So we start with our model. We used Gaussian naive Bayes, but you can use any other model you want. You can use random forest, logistic regression, or any classification model. We fit our model in classical way. So I assume the user already has fit the model. Of course, you can fit the model inside MAPIE classifier, but in this case, we presume that you already fit your model. We wrap the model using the MAPIE classifier. We put the parameter CV equal prefit and method equal LAC, which is for least ambiguous set value classifier, which correspond to the label method. We fit our model. Here we have several values of alpha. 0.2 mean 80% confidence. We want 80% confidence. 0.1 means we want 90% confidence, and 0.05 95%. And so we do our prediction using this set of alphas, so we have Y-pred. It's just the punctual predictions, and YPS stands for prediction set. It will be array, a 3D array. So the rows are the actual data points. The columns are the labels. So if a label is selected as a binary value, if the label is selected among the prediction set, it will be 1. Otherwise, the value will be 0. And the third axis is related to alpha, because here we have several value of alpha. So each axis will be the prediction for the corresponding value of alpha. So here's just plotting functions. So we will plot our non-conformity score distribution on the calibration data set. We see like this is the non-conformity when we use 1 minus the softmax, and we see that with lower value of with higher value of alpha, the quantile will be close to 0, and so our prediction set will be smaller, because essentially the prediction set is the one the quantile is the one the non-conformity score is less than than quantile. So when you have smaller value of alpha, you want more confidence in your data, the value of a quantile will be higher and your prediction set will be higher, will be larger. Let's plot the results for the three value of alpha using the label method. So this is just the plot method. We are taking the station data set, and we have in the predicted label, the true labels, and these are the predicted labels by the model, and we have some region where we have uncertainty and some region not. So in case of alpha equals 0.2, we see that when we are uncertain, it tends to provide empty sets, sets of size 0. Why? Because the value of quantile is very low, and so we don't have softmax that are yes, so the value of quantile is very 0, and always the non-conformity score is higher than this quantile, so we are always providing empty sets. When increasing our alpha, we see that we have larger sets, and in case of we want to a confidence of 95%, we tend to see that in the most difficult region, we have the complete set of three labels. Yeah. So this image just show you that the size of prediction set varies with the value of alpha. So you need to test several values of alpha to see what's your what you want, what's to fine tune alpha based on what's the size of data sets that you want prediction set. And so in just make another two plots with the coverage score and the prediction set 1 minus alpha. So as we said, 1 minus alpha is the desired coverage. If we say that alpha is equal to 0.05, we want a desired coverage of 95%. And we see like for each desired confidence level, we have coverage, the corresponding coverage is almost more or less equal to 1 minus alpha. So coverage is when we talk about coverage, is when the true label is among the predicted labels, and we can see that it's almost always the coverage equal minus alpha, because we have theoretical guarantee that the coverage score will be equal to the desired 1 minus alpha. And the prediction set width, we see that when we ask more confidence, we want more confidence, the model will be more conservative, and it will provide larger prediction sets. Yes, so and so to plot the prediction set size distribution, so it's just a small one just to check how often we get for alpha equals 0.505, we see that most of sets are of size 1, which is very good. So it means like we are pretty sure of our prediction, but some sets are with the size 2, and some set we are size 3 because we are completely uncertain of our prediction. So this is with the first method. With the second method is adaptive prediction set. As a reminder, it's the same as the only difference is like in the non-conformity score. So instead of using 1 minus softmax, we will use the cumulative sum of softmax. And we do the same plot, exactly the same plot. We do fit of we have the same parameter. We have the estimator CV equal prefit, but just the method equal APS. And we have the fit and we have the predict. And so here we see like for smaller value of alpha with the same value of alpha for comparing to the label method, we have larger prediction set. So even with a large value of alpha equals 0.2 or small desired confidence level 80%, we have larger size data sets. And even if we we would like to have a very high confidence level, we tend to see that even the size of our prediction set become large even in region where we normally are sure about our prediction. Even in this region, the size of data set become large. Do you have questions? So in conclusion, we will resume this in conclusion later, but the APS method tends to be more conservative with the same value of alpha. It tends to give larger data sets comparing to the label method. Why is this? Because we are using cumulative softmax, and the values of cumulative softmax are always like high, so we will tend to have many values that are larger than the quantile, or the non-conformity score is lower than quantile. This is the same distribution as before. We have a distribution of non-conformity score, and we see that the non-conformity score are always high, more or less, or always the same. And we take the quantile for each value of alpha, and we see that when the alpha become very small, the quantile is not very different. It's not like the label method. If we come back to the image before, we see in the label method we have there's distance between quantile for different value of alpha, but for the APS method, changing the value of alpha a little bit will not highly change the quantile. So we have more consistent interval width among different value of alpha. And so to draw the same plot, you can see that we have always the same coverage for 1 minus alpha, but we see like for prediction set width, we have approximately a linear line which come exponential at the end, but it starts a linear line until like high value of alpha. High value of 1 minus alpha, or like lower value of alpha. To make the same plot as before, we see that we have more data points with prediction set equal to 3, and so IPS tends to have more flexibility in terms of prediction set size. The top K method is the same as the two methods before. Just for non-conformity score, we use the rank of the true label prediction. And I didn't make too much draw here just to show you that it's not running. But basically, when you run it, you will see that you will get always the same prediction set. This is the advantage of top K. If you want specific prediction set, for example, you would like to always have a 3, or you want not specific. You don't fix the size of that prediction set you want, but your quantile, this method will give you always some prediction set. Maybe it's useful in some use cases, but yeah. So it's on you to decide which is the best method to use. In resume, we have 3 methods in MAPIE. There are actually more, but 3 main methods: the label agnostic conformal method that use softmax scores or 1 minus softmax scores for non-conformity scores. The APS use cumulative softmax scores, and top K use for top K classes with high softmax, or the order of classes as non-conformity score. The effect of alpha, we see that lower alpha result in larger prediction set because we want more confidence level. So it will be more conservative and gives you more larger sets, while higher value of alpha, you want less confidence. You are like more flexible in confidence, but it will give you smaller prediction sets. In the visualization, we saw that the LAC can give you sometimes null prediction sets. You have prediction set with no label. The APS eliminates the null prediction set. If you don't accept at all null prediction set, the APS will remove this for you and produce wider sets. and the top K will generate fixed sets, fixed size prediction sets. So we also did a analysis on coverage and mean width analysis, and we see that APS provide, as before, all lag and APS both provide accurate calibration, accurate coverage, the desired coverage that we would like to have. And yeah, I don't know why we put two comparison between the method, but lag is more precise in classification boundary, may fail in ambiguous area, leading to null prediction. APS provide robust prediction and is more conservative, and top K faster, but it's like flexibility. Yeah. So now we will enter a different tutorial, which is how to use MAPIE for autoregressive model, for example, BERT. We have a use case on we are dealing with the robot, and we are giving command for this robot, and the robot should answer the command, should understand the command, make classification of the command, and if it's like we are asking him to do something precise or something else, there are several possible actions. So and if using the conformal prediction, we see that the command could be for example, if we go, I have one for, could you send this meeting details at 6 p.m. If we have several possible values, we know that we are having uncertainty, and we ask the model, we ask the user for more clarification in his instruction or command. So the use case is to use conformal prediction to check if we have larger prediction sets. This means that we have uncertainty, and ask user for more clarification. So we start, we load the data set. We have train equal 1000, carry 1000, and test 1000. This is not typical because in general you have the train data set is much higher than the calibration and test set. But for now, we just, for simplicity, we use the same size. Now we can you can load the BERT model from Hugging Face pipelines. So you take text classification, and you load the BERT model that you would like to have, and we are just making some prediction. Now, in order to use it with MAPIE, we fit we just make scikit-learn wrapper. We should implement the fit method, the predict proba, and the predict, and see that for fit we just return self, because we don't fit, we assume that the model is already fitted the estimator. We will not fine tune it or retrain the BERT model. The predict proba, just a small code on how to take the predict proba from the logits, and the predict will just take the argmax. And we run the fourth step of MAPIE. First, we get the main predictor. We define the non-conformity score. You have two options to define the conformity score, either by initializing a class called APS conformity score or lag conformity score, or by using a string. For here, we show you that we can also use a class for the conformity score. We fit using MAPIE classifier. In the fourth step, we define alpha, and we make our prediction.
Si tu peux élargir un peu la police encore. Il y a quelqu'un qui...
C'est mieux? And so for visualizing the results using BERT, so here it's clear, like we have the command. It's necessary to go to Ambershire, and the true label is move, and the predicted label is move, and so we have prediction set. It's called just one word, one value. But for other, like we have several values. So we have true label equal exchange, and we have prediction set is like contains three possible values. And so it's the case. We have only one example like this, but it tends to be because the value of alpha here, if we go back, the value of alpha is very low, so we want high confidence level, we want high coverage. So the model tends to be conservative and make even if the softmax is very low, it tends to give us conservative data sets. And because we used APS, APS tends to give larger sets. If you use the label method or the top K, maybe you will have other size of data sets. The third tutorial is about risk control. So, il reste combien de temps? 4 minutes. Okay. 15? Okay. So the last tutorial is about risk control. We will not deep dive in details, but we will just be quick here. So how does the what we'd like to have is like so what is risk control is like in a typical machine learning problem, you would like to, for example, control the precision. You would like some theoretical guarantee that your precision is sometimes is always higher than 90% or 95%. Or you have another use case where you would like some guarantee that your recall is always higher than some specific threshold. And so this is the risk control in machine learning. And in MAPIE, we will provide several methods for risk control. One of the methods is learn then test. So it's a robust approach that for controlling the precision, it can be used to control any risk. But in MAPIE, we used to control precision, but it also can be used to the framework can be used to control any type of risks. So we will talk about precision control as a risk control and why it's important. Because, for example, in medical diagnostic or fraud detection, in medical diagnostic we would like to have, for example, we want like 95% sure that in our prediction we want some theoretical guarantee that our precision will stay higher than 95 or 99%. Why it's in multi-label classification? Because there are several possible prediction values for each data point, and we'd like to have a set that such as we are sure that so we have the correct prediction inside this output prediction set. The key concept of precision control using the LTT framework. First, we calculate the empirical risk. So for different threshold, we calculate what's the precision. So for example, if we say that we want 10% threshold of the softmax. So classification, we want 10% threshold of the softmax labels. What's the precision? And we test this. We calculate this precision for all values of possible threshold. And what we would like to have is the risk, or we would like probability that the risk is lower than alpha is higher than one, for example, 1 minus delta, which could be 90%, or we want to be 95% sure that our risk is lower than alpha. Here, when we say risk is like 1 minus the precision, so we want our precision to be higher than certain value with some confidence of 1 minus delta. The learn then test procedure, how it's done. First, as we said, that we have the learning phase. We have multiple threshold candidate, and we calculate the empirical precision risk for each candidate threshold. And in the testing phase, we will select only the threshold that satisfy the condition that we want to satisfy, that the empirical risk or the precision is higher than certain value. But also we will have another procedure, which is family-wise error rate, that we used also to keep the threshold that also respect this family-wise error rate. And if you want more detail, you can deep dive into the article. I will not enter the details of how this is used. The advantage of LTT is can be used for non-monotonous loss function. For the precision is not always monotonically increasing. We see later that the precision is not monotonically increasing. It's like a curve that could be increasing in some region and decreasing in some region depending on the value of alpha of lambda. Sorry, and we have flexible threshold selection, and because it gives you not one threshold but many threshold possible value of threshold, and we have statistical guarantee for LTT. So as before, we are importing the library. We're creating the data set as before with the centers and some covariance, and we are using multivariate normal distribution to sample the data. And we have here a data set with 7 classes, and we are fitting the multi-output classifier using Gaussian naive bias, and we are using MAPIE multi-label classifier with the method LTT, and the metric control is the precision. And here we will draw the value that are selected by MAPIE. So first we have the MAPIE draw the line. In the LTT framework, you are doing 2 type of filtering. You test the precision or the risk for all possible value of threshold. Then you pass through the first filter where you would like your empirical risk to be higher than certain value, lower than certain value. So you filter out all alpha that are higher than this, or lambda that are higher than this value, and then you pass through a family-wise error rate, and you keep also only small set of candidates among possible values of lambda. Here the last set is between 0.7 and 0.85, and so you can choose any value of any lambda between among these values that with any lambda among these values, and will have your theoretical guarantee that your risk will be I don't know what we defined the delta. So we said that alpha, sorry, I moved faster, but we said that alpha is equal to 0.1 and we want delta to be 0.1. So we would like to know that our precision is higher than 90%, and is higher than 90% with the guarantee of probability 90%. So if you choose any alpha value between these two, your precision will be higher than 90% with the probability of 90%. So I will stop now. I hope I was clear. It's a long session. So...
Il nous reste 7 minutes, mais du coup, on peut définir là si...
Oui.
Demander si les gens ont encore des questions.
If you have any other question, you can feel free to put in the chat, but otherwise we finished.
Tu veux que je finisse? Tu veux que je fasse
Yes.
une conclusion?
Oui.
Je te mute. Okay, Valentin back on the audio. So thanks everyone for attending this tutorial. We hope we have been clear and have given you an overview of what you can do with conformal predictions and how to do that using MAPIE. So maybe Conrad, if you want to add a quick word to wrap it up.
Yeah, thanks to you both. Thanks, Valentin, and thank you, Hussein. Just to wrap up, thank you everyone again for joining. And if you want to continue the discussion, we do have a Discord, PyData Global Discord. The link should be available in the AirMeets area homepage, and a recording for the session will be available shortly afterwards for rewatching. So thank you again, and see you at the next PyData Talks. Thank you.